Section: Introduction. In this section, we discuss the recent progress in large language models, LLMs, which marks a major advancement in artificial intelligence. Models like ChatGPT, Gemini, Opus, and Llama 3 show reasoning abilities that are close to average human performance in various areas. These advancements have expanded the use of LLMs beyond simple chat and text tasks to more active roles, where they can autonomously perform actions in environments such as coding, device control, and web applications. However, challenges remain, particularly in how well LLMs can generalize in interactive, multi-step situations, as they are not specifically trained for these tasks. This issue persists even in top models like GPT-4. While there is growing research aimed at improving agentic capabilities, much of it focuses on enhancing existing models through prompt-based learning or limited fine-tuning, which restricts their reasoning and decision-making skills. Reasoning and planning are recognized as key difficulties for current LLMs. Although there have been efforts to enhance these skills through prompt-based methods, they are still limited by the underlying model's performance. Some research has looked into fine-tuning and combining it with search prompting to provide detailed feedback. Other studies have utilized search algorithms alongside optimization techniques to significantly improve capabilities, especially in solving math problems and generating code. In our work, we aim to enhance the planning and reasoning abilities of a web agent that interacts with a real-world website. Our objective is to create a method that allows the agent to learn from its experiences with minimal supervision. Previous studies have shown that strong reasoning is crucial for the performance of autonomous agents, especially since they need to understand how their actions impact their environment. To achieve this, we introduce Agent Q, a new approach that integrates key concepts of reasoning, search, self-critique, and reinforcement learning. We draw inspiration from Sutton's idea about the effectiveness of general-purpose methods that improve with more computation, highlighting the advantages of combining search and learning. We implement a Monte-Carlo Tree Search (MCTS) strategy to guide the agent's exploration of web pages. Given the complexity of the environment, we use a base LLM to generate possible rationales and actions. While this basic search strategy improves success rates, it still faces challenges with long tasks due to sparse rewards. A small error can lead to incorrect final outputs, complicating credit assignment. To address this, we incorporate AI feedback and self-critique, prompting the LLM to provide self-evaluation at each step, which acts as an intermediate reward and helps direct the search. Although this enhances the agent's success rate, it requires extensive online interactions and the ability to reverse actions, which isn't always feasible in real-world scenarios. Autonomous online searches with minimal supervision can lead to unreliable agents that make mistakes, posing risks in sensitive situations like banking or sharing private information. To mitigate this, we leverage the traces from the search process to enhance the model's capabilities by learning from both successful and unsuccessful attempts using offline reinforcement learning with the direct preference optimization (DPO) algorithm. We establish preferences at the node level, scored based on AI feedback and the success rate of each explored path. We test our approach on the simulated webshop benchmark, a mock e-commerce platform, and a real-world booking website, using Llama 3 to 70B as our base model. In the webshop environment, our method consistently outperforms behavior cloning and reinforcement learning baselines, even surpassing average human performance when enabled with online search. In our real-world booking tests, Agent Q boosts the model's zero-shot success rate from 18.6% to 81.7%, a 340% increase, outperforming GPT-4 after just 1 day of autonomous data collection. With online search capabilities, our success rate further rises to 95.4%. We believe our approach significantly advances the development of autonomous web agents through its search and self-critique features, establishing a new standard for reliable decision-making in interactive environments. Section Summary. In this section, we discuss the advancements in large language models, LLMs, and introduce Agent Q, a novel approach that enhances planning and reasoning capabilities for autonomous web agents through a combination of search, self-critique, and reinforcement learning. Our method significantly improves success rates in complex environments, outperforming existing models and setting a new benchmark for multi-step decision-making. Section: Related Work. In this section, we discuss various research areas related to our work on agent design, self-improvement, reasoning, and reinforcement learning. We provide a brief overview of these related works. First, we note that recent large language models, LLMs, have shown promising abilities in reasoning and planning. We can trigger these behaviors in strong models using simple prompts, which we incorporate into our agent design. Another area of research involves step-by-step verification methods, known as process reward models, particularly for mathematical reasoning. While these models enhance performance beyond outcome-based training, they require significant human effort for labeling steps. Some recent methods have introduced self-supervised techniques for this step-level supervision. Concurrent studies have also explored tree-based search methods combined with direct preference optimization, DPO, training for math reasoning. Our approach aligns with self-supervised search methods and incorporates AI feedback to guide intermediate steps, marking our first attempt to apply this in a realistic agent context. Other works have utilized the base model's zero-shot capabilities without further training and have been limited to simulated environments. We build on the training methodologies from previous studies to enhance our agent's zero-shot performance. Next, we highlight the advancements in autonomous web agents, driven by the capabilities of recent pre-trained large language and vision models. These models have improved code understanding and context handling, enabling agents to navigate complex environments effectively. Strong reasoning and planning abilities have led to the creation of several promising agents. While some recent works have focused on enhancing agent-specific performance through online exploration and error correction, most still rely on existing models like GPT-4v with limited fine-tuning. Our work emphasizes the importance of model training for ongoing improvement. We integrate a planning and reasoning agent with Monte-Carlo Tree Search, MCTS, for inference time search and self-critique to collect data for reinforcement learning training. In the realm of reinforcement learning, we recognize its critical role in training modern generative AI systems. Traditional methods often use the proximal policy optimization (PPO) algorithm, which can be complex and requires many online samples. This is particularly challenging in risky scenarios where agents might make significant mistakes during training. Offline reinforcement learning algorithms like implicit language Q learning and the Q transformer are designed for autoregressive models and can be trained safely on pre-collected datasets, but they haven't been effectively scaled to modern LLMs. While some methods have successfully framed the reinforcement learning problem at a step level, they still involve high complexity and auxiliary models. Therefore, we choose to use the direct preference optimization (DPO) algorithm for its simplicity and suitability for our tree search data. We then outline the basics of our agent training process. We adopt a general partially observable Markov decision process (POMDP) framework, which includes observation, state, action spaces, transition dynamics, and a reward function. This framework is ideal for modeling web interactions, as it accommodates the exploration of unfamiliar environments and the dynamic nature of the web, which often leads to partial observability. Our agent's observations consist of user commands and browser information, starting with a user instruction followed by web pages in HTML format. The agent's actions are based on its history, employing a React approach with an initial planning step. For the first action, we utilize the LLM's planning capabilities to generate a sequence of steps in language. Subsequent actions involve reasoning steps and browser interaction commands, which include options like clicking, scrolling, typing, or asking the user for input. After generating the environment action, we prompt the model for an explanation action, creating a composite action that includes planning, reasoning, environment interaction, and explanation. When optimizing our models, we consider the joint likelihood of the initial action and subsequent actions, unlike some previous works that downweight reasoning likelihood. The agent state reflects the current web state, which may not always be observable. We also build an agent memory component, using a compact history representation that includes the actions taken and the current browser state. This approach allows us to maintain a manageable context while still capturing the agent's intentions and decision-making process. Although only the environment action interacts with the browser, the planning, reasoning, and explanation components influence future decisions. Thus, we compute likelihoods over the composite action during optimization. Section Summary. In this section, we provide an overview of related research in agent design, highlighting advancements in reasoning and planning using large language models, LLMs, the development of autonomous web agents, and the integration of reinforcement learning techniques. We emphasize our unique approach that combines planning, reasoning, and self-critique to enhance agent performance in dynamic web environments, while also addressing the challenges of training and optimizing these agents effectively. Section: Fine-tuning language models from feedback. In this section, we discuss fine-tuning language models using feedback. Traditional methods for reinforcement learning from human feedback, RLHF, treat the model as a policy and aim to optimize a specific objective while avoiding deviations from the original model. This approach can be applied to complex tasks, like retrieving information through web navigation. However, classical RLHF methods, such as proximal policy optimization, PPO, can be complicated and require costly online data collection, making them less practical for general web tasks. We explore reinforced fine-tuning, RFT, algorithms, which have gained traction for their simplicity and scalability. These methods gather data and filter out less optimal samples based on a reward model, creating a dataset of high-quality experiences. We then perform standard supervised fine-tuning using this dataset, applying a divergence penalty by limiting training rounds. While effective, these methods often fall short compared to traditional RL techniques, especially in text generation and reasoning tasks. We primarily use them as baselines for our understanding. Next, we introduce direct preference optimization, DPO, an offline RL method that does not require online data collection. DPO focuses on pairwise comparisons of responses to a single prompt, determining which response is preferred. Although initially designed for simpler settings, we adapt it for more complex scenarios. A challenge with DPO is the need for a reference model during optimization, which can be resource-intensive. To address this, we modify the algorithm to use an off-policy replay buffer that collects trajectory data and likelihoods, removing the need for a separate reference model. We also present preliminary experimental results to establish a foundation for our future work. We utilize the Agent Ohana XLA-MV0.1R model, which is fine-tuned from a pre-trained model on various agent tasks, including data from WebShop. We maintain the same agent configuration as previous work for a fair comparison. Our evaluation occurs in the WebShop environment, where the agent must locate specific products among 12,087 predefined tasks. We split these into a training set of 11,000 tasks and a test set of 1,087 tasks for zero-shot evaluation. Our findings show that the base XLA-MV0.1R model achieves a success rate of 28.6% on test tasks. We observe that further RFT training improves this rate to 31.3%, a modest increase. Next, we fine-tune the base model using the trajectory-level DPO algorithm, which leverages successful trajectories over failed ones, resulting in a significant performance boost to 40.6%. We also test this model with beam search for action generation, which offers only slight improvements. Despite these enhancements, our agents still struggle to reach average human performance in this environment. We identify a key issue. The DPO policy tends to execute a greedy search for product matches, often limiting itself to the first page of results instead of exploring further. This indicates a weak exploration strategy that hinders overall performance. Section Summary. In this section, we explore various approaches to fine-tuning language models using reinforcement learning from human feedback, RLHF, highlighting the limitations of classical methods like PPO and the advantages of alternatives such as reinforced fine-tuning, RFT, and direct preference optimization, DPO. Our preliminary experiments demonstrate that while DPO significantly improves agent performance in a web navigation task, challenges remain, particularly in the model's exploration strategy during product searches. Section: Agent Search. In this section, we explore enhancing the agent search capabilities using Monte-Carlo Tree Search, MCTS. We found that while training with outcome supervision through DPO improves performance, the model still falls short of human-level capabilities due to limited exploration. We implement the MCTS algorithm, which consists of 4 key phases: selection, expansion, simulation, and backpropagation. Each phase is essential for balancing exploration and exploitation while refining our policy. We treat the web agent's actions as a tree search over web pages, where the state includes a summary of the agent's history and the current web page's structure. Unlike fixed board games, our action space is open and variable. We use our base model to propose actions and sample a set number of possible actions at each web page. After selecting and executing an action, we move to the next web page, updating our history to form a new node. During the selection phase, we apply the upper confidence bound (UCB1) method to choose nodes, aiming to balance exploration and exploitation. We denote the agent state as h_t and consider the value function q, h_t, a, which estimates the success chance of taking action A in state h_t. For each new state, we sample k proposed actions from our base model and initialize their values to 0. Since the web environment lacks intermediate rewards, we use AI-based feedback to guide our exploration. We rank the proposed actions based on their utility in completing the user task, iteratively refining our selection until we have a complete ranking. After selecting actions, we explore them using the UCB1 formula, where n, h_t, indicates how often state h_t has been visited, and c_xp is a constant for exploration. For each rollout, we start at the root node and follow the child states that maximize the UCB1 score until we reach a leaf node, repeating this for each prompt in our batch. In the expansion phase, we execute an action in the browser to reach a new page. We then roll out the trajectory using our current policy until we hit a terminal state, receiving a reward at the end. We backpropagate this reward, updating the values of each node from the leaf to the root. Each state node tracks 2 values: the average reward for passing through that state and the number of times that state action pair was visited. To improve our zero-shot performance, we recognize that training large models with offline reinforcement learning is challenging, and online reinforcement learning isn't scalable for real interactions. We adopt a recent approach that applies the DPO algorithm at the step level for multi-step reasoning problems. Our method is similar to previous works that utilize tree search to create step-level preference pairs. We generate a dataset of preference pairs, ensuring both actions were explored, and optimize the DPO objective at the node level. We can modify existing theoretical results to fit the interactive nature of our web environment, allowing us to approximate the optimal reinforcement learning policy by generating preferences based on the value function. Since success outcomes provide limited guidance, we also incorporate process supervision through AI feedback. We interpret the model's action rankings as driven by an implicit value function. This self-rewarding approach has shown promise in reinforcement learning from human feedback, and we apply it to our agent. We compute the state action value as an average of the empirical value estimated through MCTS backpropagation and the value based on the AI model's rankings. We then create preferences over action pairs that exceed a certain value threshold, outlining our reinforcement learning approach. Section Summary. In this section, We enhance the agent's performance by integrating Monte-Carlo Tree Search, MCTS, to improve exploration capabilities, allowing the agent to navigate web pages more effectively. We utilize AI-based feedback to guide action selection and incorporate reinforcement learning techniques to optimize decision-making based on the agent's interactions with the web environment. Section: Full Webshop Results. In this section, we present the complete results and comparisons. We observe that adding search capabilities during testing significantly increases our success rates from 28.6% to 48.4% when we apply Monte-Carlo Tree Search, MCTS, to the base XLAMV0.1R model. This performance is close to the average human success rate of 50.0% and surpasses the zero-shot performance of the DPO model trained with outcome supervision. By fine-tuning the base model as described in our algorithm, we achieve a further improvement of 0.9% over the base DPO model. When we use MCTS on the trained Agent Q model, we see performance rise to 50.5%, slightly exceeding average human success rates. We conclude that the ability to search during testing represents a significant shift from zero-shot agents, even those with extensive reinforcement learning training. Additionally, while dense-level supervision shows some improvement over outcome-based supervision, the gains are modest in the webshop environment due to its requirement for shorter task trajectories, allowing the model to learn effectively from outcome supervision alone. We plan to investigate more complex real-world environments that necessitate longer credit assignment. Next, we explore scaling the Agent Q framework to real-world applications, specifically for making bookings on OpenTable. Our initial tests with the XLAMV0.1R model were unsuccessful, achieving a success rate of 0.0%. We then switched to the Llama 70B Instruct model, which showed some initial success. In the OpenTable environment, our agent's task is to book a restaurant reservation. It must locate a restaurant page, check for availability on a specified date and time, select seating options based on user preferences, and enter user contact information to complete the booking. Since OpenTable is a live platform, we use the GPT-4v language model to assess performance based on specific criteria: correct date and time, accurate party size, proper user information entry, and successful reservation completion. A task is considered complete only if all these conditions are met. We also tested using Llama 70B for outcome supervision but found that vision capabilities significantly enhance success rates, as confirmed by human validation. Currently, we use GPT-4v due to the lack of a suitable open-source vision language model. We anticipate that as more multimodal models become available, we can transition to a fully self-supervised approach. To create queries for the OpenTable benchmark, we programmatically generate a variety of user requests by combining restaurant names, desired dates and times, and user information. Navigating live websites presents numerous challenges. For instance, if a user requests a restaurant in a different city, the model must take extra steps to locate it. If the exact date and time are unavailable, the model needs to select the closest option. Additionally, if users have preferences like indoor or outdoor seating, the model should engage with them to determine the best choice. OpenTable poses complex challenges for web navigation agents, requiring an average of 13.9 steps to complete a task, more than double the 6.8 steps needed for WebShop. For the observation space, we design an intermediate state representation that extracts relevant visual components from the website's raw HTML and highlights interactive elements. The agent can perform actions such as clicking, going to a URL, typing, submitting, clearing, scrolling, and asking for user help. In our OpenTable experiments, we utilize the Llama 3-70B Instruct model as the initial policy. We find that this model's superior reasoning abilities are essential for effective task completion, enabling us to generate diverse success and failure trajectories to improve the policy. Regarding our results on OpenTable, the base XLAMV0.1R model achieves a success rate of 0.0% due to its inability to follow general web navigation instructions, unlike the simpler observation and action space in WebShop. By initializing the base policy with the Llama 370B instruct model, we achieve a zero-shot success rate of 18.6%. After one round of reinforcement fine-tuning on 600 successful trajectories, we improve the success rate to 67.2%, surpassing the zero-shot performance of the GPT-4o model, which stands at 62.6%. We adopt the RFT model as our reference policy due to the low success rate of the original Llama 370B instruct model. In this environment, training with outcome supervision alone improves performance by 4.6% to 71.8%, but it still falls short compared to the full agent queue pipeline, which achieves a zero-shot success rate of 81.7%. We believe this is because OpenTable is a more challenging environment, requiring nearly twice as many steps as WebShop, thus benefiting from detailed supervision and credit assignment. We also examine the impact of intermediate AI feedback during training and use MCTS with online queue values based solely on outcome rewards. This approach still outperforms trajectory-level DPO training, achieving 75.2% compared to 71.8%, likely due to the finer credit assignment provided by the branching tree search. However, zero-shot performance remains lower than when using intermediate process-level supervision, with the full agent queue achieving a 6.5% higher success rate at 81.7%. Similar to our WebShop findings, we see an increase in capability when allowing the model to search during inference, with the base RFT model reaching 84.3% success with MCTS, outperforming the agent queue's zero-shot performance of 81.7%. When we conduct additional MCTS searches using the agent queue model as the base policy, we achieve a remarkable success rate of 95.4%. Section Summary. In this section, we demonstrate that incorporating search capabilities significantly enhances the agent's success rates in both the WebShop and OpenTable environments, with the agent queue model achieving up to 95.4% success through fine-tuning and MCTS, compared to lower rates with simpler models. We also highlight the challenges of navigating live websites, which require more complex interactions and longer task completion steps, necessitating advanced reasoning and supervision techniques. Section: Discussion. In this section, we developed algorithms that enable web agents to improve themselves with minimal human oversight. Unlike previous works that build on existing models without further training, we focused on fine-tuning pre-trained models specifically for web navigation tasks using synthetic reasoning and search data. While we achieved notable enhancements in our model's abilities within our target area, several research questions still need to be addressed. One major challenge we face is the limited reasoning skills of our web agents, which restrict their exploration and search strategies. To tackle this, we employed process-level supervision from a separate critic model that helps rank potential actions for the agent. This differs from mathematical reasoning approaches, where models typically classify the correctness of individual steps, and from other agent models that use zero-shot value functions. Although we dedicated considerable effort to training the agent's policy, we kept the critic model unchanged, which may also benefit from further fine-tuning. We plan to explore these design choices in future work. We chose the Monte-Carlo Tree Search (MCTS) algorithm due to its previous success in reasoning tasks related to math and code. However, agents using MCTS in real-time environments may need to engage in many risky interactions, suggesting that a different search strategy could be more effective. Recent studies have proposed learning optimal search and exploration methods for reasoning tasks through meta-reinforcement learning, which we see as a promising direction for future research on autonomous agents. We also noticed a significant difference between the performance of zero-shot agents and those equipped with search capabilities, similar to findings in recent studies on code and reasoning. We aim to investigate these trade-offs on a larger scale and examine how different search and optimization methods impact performance. Regarding online safety and interaction, our agent design allows for mostly autonomous exploration, self-assessment, and improvement with limited human input. However, the agent may make numerous mistakes during its search, which can be challenging to correct, especially in safety-critical online activities like communications, payments, and filings. This limitation restricts the types of websites where our agent can be safely deployed, and we may need to implement additional safety measures and human-in-the-loop training setups.